Hello, and welcome to our lecture on equations involving logarithms and exponents. In the last few lectures, we've developed the exponential function and its inverse, the logarithmic function. And we noticed that base 10 and base e were the most important bases for these functions. Well, now, today, I'd like to look at equations involving logarithms and exponents and see how to solve some of these equations. And then we'll see an application to dealing with heights of humans near the end of the lecture. So let's recall some of the important properties of logarithms that will play a big role today. Here's a list of them. For example, a to the x equal a to the y is equivalent to saying x equals y. That's because the exponential function is 1 to 1. And in the same way, if the logarithm base a of x equals the logarithm base a of y, then x equals y, because again, the logarithmic function is 1 to 1. Those inverse properties will come into play. A to the power log x is the same as x, as long as the logarithm in the exponent is also to base a. And in a similar fashion, logarithm base a of a to the x equals x. Those are the inverse properties of logarithms and exponents. And another property we'll use a little bit today is that the logarithm of x to the power b is the same as b log x. You can move the b down into the front of the logarithm. And all these properties hold for logs to any base, and in particular base e. Let's do some examples. Let's play with these formulas in solving some equations. So here's a fairly simple equation involving exponentials. Suppose you're asked to solve 4e to the 2x minus 3 equals 2. In other words, for which x values is this equation true? Let's find x. Here we go. Well, the obvious thing to do, first of all, is move the 3 to the other side, and we have 4e to the 2x equals 5. And now divide by 4, and we have e to the 2x equals 5/4. Now, some of you might be able to jump right away to the equivalent logarithmic equation related to this equation, e to the 2x equals 5/4. But I'm not that comfortable. Here's what I usually do. I usually take logarithms of both sides. So I have log of e to the 2x and then the logarithm of 5/4 on the other side. And then I say the following, log e to the 2x, those are inverses of each other, and the left-hand side is just 2x, and the right-hand side is still log of 5/4. But again, some of you might have jumped and didn't have to take logs of both sides. Both are correct. And finally divide by 2, and we have x equal 1/2 log of 5/4, which is approximately 0.11. Now, I've talked about this earlier, but it's worth repeating. There are many ways of writing the correct answer. I mean, look at this previous problem. It had, the final answer was 1/2 log of the quotient 5/4. I can think of lots of ways of rewriting this answer. Here are a few of them. You could write it as log of 5/4 to the 1/2 power. We could change the 1/2 in the exponent to the square root symbol, and it would be log of the square root of 5/4. Or we could take the square root of that quotient and write it as log of square root of 5 divided by 2. The square root of 4 is 2. And even another way, we could write log of 5/4 as log 5 minus log 4, using that property that the log of a quotient is the difference of the logarithms. What's the moral of the story here? There are lots of ways of writing the correct answer, and the answer you obtain on a problem might look different than the answer that another student obtains or the answer in the back of the textbook. Okay, good. That was a pretty easy equation to solve, I think. Let's look at a more interesting one. When mathematicians say more interesting, what they really mean is more difficult. But here we go. The equation is e to the 2x minus 3e to the x plus 2 equals 0. And again, we're asking for find all x values that make this equation true. In other words, where does the function e to the 2x minus 3e to the x plus 2 cross the x-axis? What are the zeros of this function? Well, it's not clear how to start, is it? You're sort of looking at that and go, well, I'm not sure what to do, help, help. Well, notice the following. E to the 2x is the same as e to the x squared. That's one of those properties of exponents. So now I can write this as e to the x squared minus 3e to the x plus 2 equals 0, and think of it as a quadratic polynomial. But it's not a polynomial in x. It's a polynomial in e to the x. Isn't that cool? This looks like a quadratic, except the variable now is e to the x. So I can factor it. I can factor this quadratic. It's e to the x minus 2, the first term, times e to the x minus 1, and that's equal to 0. You can check my work, multiply out that factorization, and you'll come back to the original polynomial. Okay, if the product of two factors equals 0, one of them is 0 or the other one's 0. So if e to the x equals 2, that's setting e to the x minus 2 equal to 0, then using the inverse properties of exponentials and logs, that means that x is log 2. And if e to the x is 1, that means that x is log 1 or 0. So I see here two solutions. X can be 0 or x can be log 2. And I invite you, as I usually do, graph this function and see where it crosses the x-axis. You'll see that it crosses at 0 and at log 2, which is about 0.69. All right, good going. That was a hard equation, I thought. Had some tricky quadratics kind of hiding inside. Here's another equation, and now we'll be using logarithms here. And it's an equation involving logarithms. The first one's pretty simple. How about 5 plus 2 log x equals 4? What's x? Well, obviously move the 5 to the other side, and we have 2 log x equals minus 1. Now divide by 2, and we have log x equals minus 1/2. Okay, what to do? Again, some of you will immediately jump to the equivalent exponential equation. When you see a log equation like that, you can immediately move to the corresponding exponential equation. But again, I'm not as comfortable with that as others. And what I like to do is take the equation and raise both sides to e. In other words, e to the left-hand side and e to the right-hand side. So it's e log x equals e to the minus 1/2. So both sides have been raised to the power with e being the base. And now e log x is just x by inverse properties, and I have x equals e to the minus 1/2, which if you punch on your calculator, you'll discover is about 0.61. Let me make a comment about that answer. As a teacher, if I usually allow calculators when I'm on tests for students. They bring their calculators in, and I don't mind that at all. In fact, I encourage calculator use. I think it's great for students to be able to check their answers and verify solutions and look at a picture, etc. But I am a stickler for the following. If a student solves this problem on a test and writes the answer as 0.61, I'll take off a few points. And here's why. The answer is not precisely 0.61. That's an approximation. The exact answer is e to the minus 1/2. So if I had asked for the exact answer, which I usually do, they've got to write down e to the minus 1/2. If I asked for an approximation to 2 decimal digits, then 0.61 would be fine. Okay? Please ask your teacher if they accept calculator answers. It's kind of a interesting discussion to have with a teacher these days because calculators have changed the way we do mathematics so much. All right, let's turn now to a logarithmic equation that will point out some of the pitfalls that occur when you're solving these equations. This is a neat problem. I think you'll like it. It's solve for x, of course, and here's the equation. Log of the quantity x minus 2 plus log of 2x minus 3 equals 2 log x. And I'm using the natural logarithm here. Okay. At first glance, panic sets in. How am I going to attack this equation? How am I going to find x? Well, let me show you some tricks. The left-hand side is the sum of logarithms. And the property is that we talked about last lecture, the sum of logarithms is the log of the product. So the left-hand side simplifies to the logarithm of a product. And that product has two terms, x minus 2 times 2x minus 3. So the left-hand side looks good now. It's the log of a product. How about the right-hand side? That's 2 log x. Oh, but I can move the 2 up to the exponent. That's the same as log x squared, as long as x is positive, of course. All right, so now I've simplified this so that I have log of something equals log of something else. And remember, the logarithm is a one-to-one function. The two sides must be equal if I cancel the word logarithm. And now I'm down to a polynomial equation. Magic! The left-hand side is just x minus 2 times 2x minus 3, and the right-hand side is just x squared. We've deleted the logarithms. All right, let's multiply out this polynomial. I think it comes out to be 2x squared. 2 times 2 is minus 4 minus 3 is minus 7x plus 6 minus 2 times minus 3. And then on the right-hand side, we have the x squared. Bring the x squared over to the other side, and we have a quadratic. X squared minus 7x plus 6. We want that to be 0. Well, I made up the problem so it can be factored. As we say, I'm a nice teacher. So let's factor it. It's x minus 6 times x minus 1. And you can check that factorization by multiplying it out. So if a product of two factors is 0, either x is 6 or x is 1. Those are the two solutions. Wait a minute. Hold on here. Is this right? Look at the solution 1 for a moment and plug it back into the original equation. What's the log of 1 minus 2? Uh-oh, negative number. The solution x equals 1 is incorrect. It's not a solution. This is called an extraneous solution. Somehow, when we did these operations, we introduced a solution that really isn't there. Now, it turns out 6 is a solution. That one's no problem, but 1 is not a solution. There's a moral to the story here, of course. Check your answers. When you finish a problem, plug in your proposed answers back into the original equation. Make sure you did it right. Not only because you might have made some arithmetical mistakes, you might have said 2 plus 2 is 5 or something, but you might have introduced these extraneous solutions doing all these operations. So please get in the habit of checking answers. Okay. For instance, what do you do on a test? I've had the following experience many times with students. I'll give a test for 50 minutes, and I have 30 students out there, and within a half an hour, a few students start turning in their tests. I'm finished, professor. And I I don't say anything, but a lot of times these students could have spent an extra 20 minutes checking their answers, because sometimes they work so fast, they're so smart, they're so fast, but they make sort of dumb mistakes. Checking answers, great advice for any student. All right, let me show you another really interesting problem, and it will bring up another point about extraneous solutions. Here's another equation involving exponential functions. E to the 2x minus e to the x minus 2 equals 0. We're supposed to find the solutions, or equivalently, the zeros of the function. Where does it cross the x-axis? Well, again, you can factor this. Remember the trick. We're thinking of e to the x as the variable, and this is e to the x squared minus e to the x minus 2. So it factors as e to the x minus 2 times e to the x plus 1. Again, you can check that factorization. Okay, let's set each factor equal to 0. E to the x equals 2. That means that x is log 2, which is about 0.7. 693. And the other factor, e to the x plus 1 equals 0, means that e to the x is minus 1. Uh-oh. What do we say here? Well, remember, e to the x, the graph is always above the x-axis. It never goes below, and so e to the x minus 1 is impossible. So there's really only one solution here, log 2. That's the only solution to this equation. It crosses the x-axis once and only once. Let's verify it with a graph. And you could do this graph on your graphing calculator and mimic what we just see here. Here's a graph of e to the 2x minus e to the x minus 2. Notice that it crosses in between 0 and 1. We could use the intermediate value theorem to say, oh, I know there's a root in between those two numbers because the graph is negative on one side and positive on the other side. It must cross in between. But notice it doesn't cross again. Here's another subtle question for you, and I'll let you think about this. Does this graph have a horizontal asymptote? Does it have a horizontal asymptote? It kind of looks like it does. That piece seems to be going off there to, well, when x is negative, large negative, the value seems to be around minus 2. Do you see why that's true? Look at the original equation. When x is negative, those exponential terms tend to 0. And the only survivor, really, is the minus 2 part of the function. So indeed, there is a horizontal asymptote here. Okay, we've solved some equations, and we've seen some of the tricky things that can happen when you don't have a solution. You have one of these extraneous solutions that pops in. Some equations, unfortunately, cannot be solved, as we say, by hand. You can't get an answer that says x equals blah, 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 blah. And in fact, in real-life applications, the equations are so complicated, probably, that you won't be able to solve them explicitly for the unknown x. Let me show you a simple example of that. Suppose you have the equation log x equals x squared minus 2. Find x such that log x equals x squared minus 2. Well, here's what I claim, and you can try all you want to show that I'm wrong. But I claim you cannot fiddle with this equation and do all kinds of tricks and finally get to the point where you have an equation that says x equals blah, some answer. You can't get x all by itself on one side of the equation. You might try it for a while, but trust me, you won't be able to do it. So here's an example where you really have to use a calculator or a computer. Okay? So how would you do it? Well, if you want log x to equal x squared minus 2, turn that into a function. Say log x minus x squared plus 2. In other words, bring one side over to the other. Call that function f of x and graph it. Graph it on your calculator. The zeros of that function will be the solutions to the equation. Now, we won't get exact solutions. We'll get approximations. All we can hope for here are approximations. And so I did this. Here's a graph of that function, log x minus x squared plus 2. And I've graphed it on a graphing calculator. And let me talk a bit about this graphing calculator screen we're seeing here. The horizontal line starts at minus 0.2 and goes out to 1.8. And the vertical is minus 2 to 2. Those are the dimensions of the window of your graphing calculator. And in that window, the important features of the function are appearing. And it looks like there are 2 zeros, doesn't it? It seems to cross twice. And again, you could use that fancy intermediate value theorem to actually say, yeah, it's negative here, it's positive here, there has to be a root in between. And if you use a calculator and you zoom in on those zeros, or you use a feature on your calculator called root, it'll give an approximation. And my calculator told me that the roots are approximately 0.138 and 1.564. So try it on your own and see if you get the same approximations. Okay, good, good. I always like to have you be the teacher. Let's play that game again. You be the teacher. And here's why this is an easy one, but I'm going to make it worse in a minute. A student comes up and says, Professor, I'm doing this test, and I've come to this part of the test, and can I use this property? Is log of x all squared? In other words, you square log x, the entire thing. Is that the same as 2 log x? Can I use that property, Professor? What do you say to the student? Well, here's what I would say. I'd say, sorry, no, it's not. That's not the right property. Remember, you can move the exponent of log x squared if the parentheses are around the x squared, not around the whole thing. But then I would be even worse for the poor student, or as I say, I would pose something to the student that's kind of fun. I'd ask the student, hey, that property's not true in general, but is it sometimes true? That's a great question, I think. Are there some values of x for which that equation is true? And the student would, of course, go, 1. If x is 1, both sides are equal to 0. And then I go, right. Is there a second value? And the student would then go, I don't know. Well, work on this. You'll find out that e squared is also a solution. Isn't that neat? So this poor student that came up to ask me a question, I sort of threw a question back to the student. That way they don't ask more questions. But wait, another student comes up and asks a similar question. Teacher, is the log base 10 of the quantity x plus 10 the same as log base 10 of x plus log base 10 of 10? And of course, we know the answer now, don't we? The log of a sum is not the sum of the logarithms. So immediately I tell the student, you got the wrong property there. That's not true. But then I torture the student by saying, is it true for some values of x? Are there some values of x for which that equation is true? Try it out on your own and see if you get the same answer I did. I got 10/9, 10 over 9, as a solution to that equation. Okay, let's do an application. And this application is a bit complicated. Complicated in the sense that the functions we're using to model the situation are pretty ugly. But that's the nature of applied mathematics. If you're going to describe the real world, you can't expect things to be so nice. But the principles that we've been developing so far will serve here as well. And this model is based on using the exponential function to describe heights of males and females. And here's how it goes. The percent m, so m is going to be a percent between 0 and 100, of American males between the ages of 18 and 24 who are no more than x inches tall, in other words, less than or equal to x inches tall, is modeled by the following function. 100 divided by, sorry about this, 1 plus e to the power minus 0.6114 times the quantity x minus 69.71. Ouch. Ouch, ouch. What a rough, what a complicated model. In a minute, I'll talk about how you get these models. Where did this come from? But for the moment, let's just accept it. In fact, not only will we accept it, we're going to play with it for a moment. So there's the model, 100 divided by that awful denominator. Let's plug in some values. Well, I'm about 6 feet tall, 72 inches. So let's plug in 72 for x. And we get 100 divided by 1 plus e to that power times, and in the parentheses, you have 72 minus 69.71. And you punch that on your calculator, and you get about 80.2%. In other words, about 80% of the adults between those age groups are 72 inches or below. So I'm pretty tall in that sense. Only about 20% are taller than me, and about 80% are my height or below. Okay. Now in that model, there's a number or an expression x minus 69.71. Let's see what that 69.71 really means. Evaluate the model at 69.71. What do you get? Well, it's e to the power in the denominator, but now that's 0, isn't it? And e to the 0 is 1. So the model collapses to 100 over 1 plus 1. E to the 0 is 1. And it's so 100 over 2 is 50%. In other words, that number 69.71 is the average height. 50% of the males are below that and 50% are above. Isn't that interesting? That sort of gives you a little indication of how they might find these models. Now, there's a similar model for American females between the ages of 18 and 24, and here is that model. I'll try to read it. It's very complicated. It looks sort of like the other one, but the numbers are slightly different. It's a quotient. 100 is in the numerator, and the denominator is 1 plus e to the following power, minus 0.66607 times the quantity x minus 64.51. Quick question. What's the average height of females between ages 18 and 24? Right, it's that number 64.51. Let's see, that's about 5 feet 4.5 inches. My wife is shorter than that, so she's below average in height, for instance. But 5 feet 4.5 inches, about the average height. Let's graph these two models. Here they are. Do not attempt to graph these by hand. Please use a graphing calculator. These are so complicated that you need a computer or a calculator to graph them. But don't they look interesting? First of all, notice that the model for F is to the left of the model for M. That makes sense because on average, males are taller than females. A couple of other interesting features. I see some horizontal asymptotes. I see one going off to the left and one going off to the right. What are they? Well, remember, the values of F and M are percentages. And so clearly the percentages are going to be between 0 and 100. And that's why 0 and 100 are the asymptotes. Okay. Bonus question. How do you come up with these models? How do they do it? Let me give you a brief look at that. It's a very complicated question. From my understanding, I've worked with applied mathematics quite a bit, and I used to work at NASA, in fact, a long, long time ago, and we dealt with ugly equations like this, ugly function with lots of decimals and things. And many times we came up with these models analyzing data. So you would gather data. For example, you might have the heights of 1,000 students between those that age interval, and then you measure all the heights of these students. And then there are computer programs that fit functions to the data. You can sometimes fit a straight line to data, you can fit a parabola to data, or you can fit these more complicated exponential functions to the data. And the computer determines those ugly coefficients that we just saw, those decimals. The computer kind of spits them out. So fitting curves to data is big business. And in fact, at my university, over in the engineering college and in the sciences, they have courses specifically for finding models for sets of data. Okay, they gather the data and then they want to model that data. Okay. Next time, I'd like to finish off our study of logarithms and exponents with a look at other models. We'll see other ways that logarithmic functions and especially exponential functions can be used to model real-life situations. And again, we'll have this problem. If you want to have an exercise or an example that looks pretty simple, then the model's not going to be too accurate. If you want a real-life model, you're going to have some ugly numbers like we saw in that last example. I'll try to balance the two for you. So next time we'll look at some real-life examples using logarithmic functions and exponential functions to model. This will be our final lecture on logs and exponents, because afterwards we'll look at trigonometry. So see you next time.